Okay, so I have an interesting scenario for you to consider. Let's say that you have a ship that is traveling at 0.90 times the speed of light. So you're going pretty fast. And then you shoot off some sort of a probe or something that shoots off at a speed. You shoot it from your point of view. Let me draw something that looks a little nicer here. You shoot it off at a velocity of 0.5 times the speed of light from your point of view. So you're out in the middle of space going 0.9 times the speed of light. You can't really tell because you're out in the middle of space. There are no reference points. And so you shoot off a probe moving at half the speed of light from your point of view. Therefore, its combined velocity, if you use Galilean and Newtonian physics, would be 1.4 times the speed of light. And we have ourselves a problem, because we just said in the last video, talking about relativistic mass and energy, that nothing can travel faster than the speed of light. So that gives us a really big question. What's going on here? Well, it turns out that you have to deal, when you're dealing with relativistic effects, then you can't just add vectors to get a relative velocity. There is a way to solve for the relativistic velocity of another object. So here we go. Let me explain this here for you. You have a rocket that's moving off at some velocity v. We're going to call that v. And then you have another rocket that moves off at some velocity u. But from the point of the rocket that launched it, we're going to call that u prime. U prime is the velocity with respect to the pilot of the rocket here, of rocket 1. Okay? So the way you calculate the velocity of rocket 2 with respect from the point of view of somebody at Earth is you take the velocity of the rocket and you add it to their perceived velocity of rocket 2, and you divide that by 1 plus v times u prime divided by c squared. Notice how this is rather similar to the gamma equation, but at the same time not. That has to do with the derivation of the equation. The square root is gone, and instead of a minus in the middle, it's a plus now. That has to do with the derivation, like I said. But you don't have to worry about the derivation. Here's the equation for you. The speed of rocket 2, which is launched off of rocket 1, is going to be the velocity of rocket 1 plus the speed at which rocket 2 is launched from rocket 1, from rocket 1's perspective, divided by 1 plus vu prime divided by c squared. Okay, so that's the relativistic velocity, and this is where we're going to be done with talking about the special theory of relativity. But before I close, let me make a couple of final comments here. There have been a lot of predictions and interesting calculations and weird phenomena that happens with the special theory of relativity. But as far as we've been able to, we've actually tested these predictions and verified that they are true to great accuracy. I gave an example with the Hadron Collider. That's one example where we actually saw special relativistic effects. And this is a good time for me to say, why do we call it the special theory of relativity? Well, because there is a further analysis of relativity, which starts to encompass more things and gets more complicated, which we call the general theory of relativity. And the cool thing about the general theory of relativity is that it can actually describe gravity and orbits and uh, why gravity works and why things move in orbits, and other things. It describes gravity in a way that no one has ever been able to. So it's really cool. We are not going to cover that in this course. But you can take your textbook. There is a chapter on the general theory of relativity further on. I can't tell you right offhand what chapter it is. I could look that up. Um, why don't I go ahead and look that up since I have it pulled up here for you. Here it is. Coming down, chapter 26 is the special theory of relativity. If we go on a little bit further, it's got to be here in the astrophysics and cosmology. There it is. Chapter 33 of your textbook talks about the general theory of relativity. Really fascinating stuff. Okay, so yes, we've been able to test special relativity and found it to be quite accurate to our normal everyday lives. The correspondence principle says that a more general theory, like special theory of relativity, must agree with a more restricted theory, like Newtonian physics, where their realms of validity overlap. In short terms, what that statement just said is that relativistic physics must agree with Newtonian physics at smaller velocities. And so that's why we don't usually see special relativity in everyday life. We're dealing with smaller velocities, which means we are dealing with relativistic physics, but since it's smaller velocities, it's the same thing as Newtonian physics. And there you go. There is a short and simple explanation of the special theory of relativity from this chapter.